Early 1945. A coastal radar station on Honshu. Japanese operators sit before their cathode ray tubes, tracking incoming formations across the dark Pacific. They have studied the patterns, American B-29, superfortresses, high and methodical, their echoes clean against the green glow of the scope. Tonight begins like the others, distant blips, growing stronger. Then, in less than 15 minutes, the screens fill with chaos. Hundreds of false returns. Wandering echoes. The operators adjust gain, switch frequencies, recalibrate. Nothing clears the picture. Master searchlights sweep aimlessly. Gun directors lose lock. The radar operators do not yet know they are facing a British invention first tested over Hamburg 2 years earlier. Metallised paper strips, each cut to precisely 27 centimeters, dropped in clouds from the bomber stream. What Tokyo believed would be a defended sky has become a blind one. This is the story of how thin foil defeated complex electronics and changed the mathematics of survival. 5th of March to 31st of July, 1943. The Ruhr industrial region lies beneath a network of invisible beams. In a Himmelbett sector control room near Essen, German radar operators study plotting tables fed by Freya early warning sets and Würzburg gun-laying radars. Each screen shows careful geometry, range rings, bearing lines, altitude marks. On the British side, at Royal Air Force Bomber Command Headquarters in High Wycombe, Air Chief Marshal Arthur Harris reviews the latest raid summary with his operations staff. Sorties flown, aircraft missing, aircraft damaged beyond repair. The numbers tell a story neither side can ignore. The German air defense concept appears elegant on paper. The Kammhuber line, named for General Joseph Kammhuber, architect of the system, stretches from Denmark to France in a continuous radar-based wall. Each Himmelbett box combines one Freya set for early warning, one Würzburg for precise tracking, searchlight batteries, and 1 or 2 night fighters. Controllers guide fighters by voice radio, calling out vectors and altitudes from their plotting rooms. German calculations suggest each box can manage up to 6 controlled interceptions per hour against dispersed bomber formations. The mathematics seem sound, the technology is proven. The RAF, they believe, will bleed itself white against this electronic fortress. British expectations in 1940 through 1941 held that night bombing would remain a relatively low-loss method to pressure German industry. Darkness would be protection enough. But by mid-1943, the numbers paint a different picture. The Battle of the Ruhr, 43 major attacks on industrial targets, has cost Bomber Command dearly. 18,506 sorties. 872 bombers lost, a loss rate of 4.7%. Over 2,000 aircraft damaged, roughly 6,000. Aircrew casualties. The Operational Research section notes in internal memoranda that this figure approaches the 5% threshold at which losses are reckoned to render the force ineffective. The Freya radar operates in the meter band, detecting targets at ranges up to 100 kilometers. The Würzburg, working at 50 to 60 centimeters wavelength, provides the precision needed for gun-laying and fighter guidance. Together, they create what German planners consider an impenetrable screen. But RAF scientists have been studying the system. Captured equipment from the Bruneville raid in February 1942 provided exact measurements. British operational researchers calculated that each Himmelbett box has limited handling capacity, only a few controlled interceptions per hour. The solution: concentrate bombers into dense streams pushing dozens of aircraft through each box simultaneously. The tactic reduces individual interception probability. Loss rates improve slightly, but remain perilously close to unsustainable levels. An RAF Air Power Review document states plainly that losses at 4.7% were perilously close to the 5% figure at which losses were reckoned to render the force ineffective. Harris has doubled his heavy bomber strength since early 1943. More Lancasters, more Halifaxes, more trained crews. But without a way to suppress German radar-guided interception, every expansion simply increases the number of crews exposed to a 1 in 20 chance of not returning on any given mission. The operational requirement crystallizes. Find a countermeasure that degrades radar-guided interception without reducing the weight of attack. The answer will come not from more armor or faster engines, but from a woman working in a laboratory with strips of metallised paper. 1941 through 1942. Telecommunications Research Establishment, first at Swanage, then at Malvern. In a TRE laboratory hut, Joan Elizabeth Struthers, a WAF physicist who will later marry and become Joan Curran, suspends various metal objects in front of an experimental radar set. On the cathode ray tube, she and her colleagues note how echo strength changes with length, orientation, and grouping. They hang wire, they try different foils, they cut strips to various dimensions. The oscilloscope traces tell a story of resonance and reflection. Before 1942, the prevailing expectation held that radar jamming would require powerful transmitters or complex electronic circuits. The technology of active interference seemed expensive and cumbersome. But the laboratory findings reveal something simpler. Strips of metallised paper, approximately 25 to 27 centimeters in length and 1.5 to 2 centimeters in width, behave as efficient dipole reflectors when cut to half the wavelength of widely used German radar sets. Released in clouds from aircraft, they produce echo strengths comparable to bomber formations. The physics is elementary. A conductor of half-wavelength acts as a resonant antenna, re-radiating received energy with maximum efficiency. What matters is not mass or power, but precise dimensional tuning. Joan Curran receives credit in post-war accounts and later biographies as the primary inventor of the British form of chaff. A. P. Rowe, director of TRE, coins the codename Window for the concept. The Countermeasures Group conducts systematic trials. Different materials. Wire proves too heavy to stay aloft long enough. Pure foil crumples and loses effectiveness. Paper backed with thin aluminum combines lightweight with adequate conductivity. Different cut lengths are tested against simulated Freya and Würzburg frequencies. The team settles on bundles weighing roughly 1 pound each, containing hundreds of strips. Drop tests from aircraft show the strips descend slowly, forming dense, long-lasting clouds of reflectors. What the British team does not yet know is that similar work proceeds independently elsewhere. Near Berlin, at the Düppel test site, German researchers develop their own version. In Japan, Lieutenant Commander Sudo Hajime of the Imperial Japanese Navy devises giman-shi, deceiving paper, using the same underlying physics. 3 nations, working in isolation, converge on an identical solution. The wavelength of radar determines the optimal strip length. Resonance physics admits no national variation. An IEE technical history summarizes the principle concisely. Chaff consists of a cloud of metal strips, each of length approximately half the wavelength of the victim radar, so that each behaves as a dipole. The language is precise because the physics is unambiguous. By early 1942, the TRE team has demonstrated that mass-produced foil strips can cheaply degrade or saturate enemy radar tracking. An expensive, sophisticated technological system becomes vulnerable to consumable ammunition measured in kilograms of paper and aluminum. The cost asymmetry is striking. Radar installations represent thousands of man-hours and scarce electronic components. Window bundles can be produced by unskilled labor in paper mills. Yet both Britain and Germany deliberately keep chaff off the battlefield. Each side fears that first use will hand the same capability to the enemy. The physics is solved. The hardware is trivial. But the political calculation remains frozen until the losses force a decision. February 1942 through July 1943. London. Air Ministry conference rooms. War Cabinet Subcommittee tables. On one side of a polished table, a TRE report describes strips of metallised paper and their experimental results. On the other side, an intelligence file details German night raids and assesses British radar vulnerability. The decision-makers understand they are holding a weapon that cuts both ways. Air Defense staff express clear fears. If Britain uses window, the Luftwaffe will immediately copy the technique and blind British gun-laying radar and early warning sets. The integrated air defense system created since 1940, the radar chain, the fighter control network, the anti-aircraft coordination, all depend on clear radar pictures. Düppel dropped over British cities could reverse the defensive advantage that stopped the Blitz. Frederick Lindemann, Lord Cherwell, Churchill's scientific advisor, counsels strongly against immediate use. The risk appears too great. Yet Operation Biting, the Bruneville raid of February 1942, has already delivered key intelligence. British commandos and paratroopers captured components of a Würzburg set from a German coastal installation. TRE engineers now possess exact measurements of frequencies and beam geometry. Analysis confirms that the German defensive network relies heavily on meter-band tracking radars, precisely the systems most susceptible to window. The technical case for using the countermeasure grows stronger. The operational case becomes overwhelming as bomber command loss data accumulates. Harris presses repeatedly to authorize window. His crews are dying at unsustainable rates. Fighter Command and Anti-Aircraft Command continue to oppose deployment. Internal memoranda circulate through 1942 and into 1943. A curious situation develops. Both Britain and Germany have developed Chaff, both understand its effectiveness, yet both refrain from using it. Each fears the other's retaliation in kind. The stalemate holds through the winter. Then the Battle of the Ruhr provides the empirical pressure needed to break the deadlock. By spring 1943, planners examining Bomber Command expansion targets against loss curves reach an uncomfortable conclusion. At 4 to 6% losses, increasing the size of the force yields diminishing strategic returns. More crews means more casualties with no proportional increase in damage inflicted. The mathematics of attrition argue for a breakthrough in survivability. In June, Churchill reviews the case. The risk of German counter-use is real, but British centimetric radar, 10-centimeter wavelength systems, will be harder for the Germans to jam effectively with simple strips. The decision is made. Window will be used operationally during Operation Gomorrah, the planned offensive against Hamburg. The acceptance of risk is deliberate and calculated. Training begins immediately. Crews of No. 76 Squadron and other bomber command units receive instructions. Throw 1-pound bundles of foil through flare chutes once per minute over Hamburg, synchronized with navigation fixes. The procedure seems almost absurdly simple. Open a packet, push it through a tube, watch strips tumble into the slipstream. But no one yet knows whether the Kammhuber line will adapt quickly or collapse under the sudden saturation. The 16-month delay between Curran's workable proposal and authorization for combat use will later be discussed in deception studies and intelligence analyses as an example of technological caution. On the night of the 24th of July, 1943, that caution ends. Night of the 24th to 25th of July, 1943. Hamburg and the surrounding German defensive zones. At RAF bomber bases across England, ground crews load window bundles into Lancaster and Halifax fuselages, stacking them beside incendiary canisters and high-explosive bombs. The bundles look innocuous, wrapped packets of what appears to be metallised paper. At German Flak Regiment command posts around Hamburg, officers review radar plots and pre-computed firing data. They anticipate another heavy raid. Recent experience from the Ruhr campaign suggests they can expect 4 to 7% bomber losses through coordinated radar-guided night fighter attacks and precision anti-aircraft fire. Bomber Command dispatches 791 aircraft. 728 attack the target. The stream follows planned routes, with crews dropping window bundles at 1-minute intervals beginning at the initial point. H-2S navigation radar and Pathfinder target marking proceed normally. But on German radar screens, the picture disintegrates. Würzburg displays fill with echoes. Controllers attempting to vector night fighters find their plots splitting, merging, and multiplying. Master searchlights, radar-guided beams designed to illuminate targets for fighter pilots, begin to wander aimlessly across the sky. Gun-laying radars lose track lock. Flak batteries fire unguided barrages into the darkness, hoping for random hits. A contemporary German technical account notes that the radar-guided master searchlights wandered aimlessly across the sky during the Hamburg attack. The language is clinical, but the implication is stark. Without radar guidance, the carefully integrated defensive system performs no better than unguided barrage fire. Interceptions depend on chance visual sightings rather than controlled pursuit. The result appears in the morning loss count: 12 bombers lost from 791 dispatched, approximately 1.5%. Far below the Ruhr average. Far below German predictions based on recent experience. The raids continue over subsequent nights. Hamburg burns. The combination of high explosive and incendiary creates conditions for the first true firestorm, convective winds reaching hurricane force, temperatures sufficient to melt glass, mass casualties among civilians. Over 1,500 die in the first night. The total death toll from the operation will exceed 40,000. But from Bomber Command's statistical perspective, the significant fact is survivability. Window works. Across multiple raids, loss rates remain suppressed. The defensive system that cost Germany years of development and scarce resources has been temporarily neutralized by strips of paper. Luftwaffe analysts scramble to understand the radar returns. Initial hypotheses range from equipment malfunction to atmospheric phenomena to deliberate countermeasures. Captured strip samples soon provide the answer. The physics is simple to replicate, but the operational balance has already shifted. While German engineers prepare their own version, Düppel Bomber Command has demonstrated that radar-based defense can be made nearly ineffective at the critical moment. The psychological impact on German controllers is as significant as the technical disruption. Trust in their instruments falters. As British crews return with unusually low casualties, the word spreads through bomber squadrons. Window works. The odds have changed. August through December 1943. Bomber Command Operational Research Section offices. Statisticians and engineers pin new raid results onto wall charts, comparing loss ratios across targets, routes, moon conditions, and dates. The chart for July shows a dramatic dip. Before window, the line hovers near 5%. After Hamburg, it drops below 2% on several major operations. The visual evidence is unmistakable. Pre-window operational thinking assumed that significant improvements in bomber survivability required fundamental changes to aircraft design: heavier armor, more defensive armament, or faster airframes. Each option carried severe penalties in range, bomb load, or production time. Analysis of post-Hamburg data reveals a different path. Loss rates on heavily defended targets have been cut by more than half without changing airframes. The difference: window plus associated electronic warfare measures, including mandrel and carpet jammers. The Operational Research section compiles comparison tables. Battle of the Ruhr. Approximately 18,500 sorties, 872 bombers lost, yielding an average loss rate of 4.7% across 43 major attacks. Early post-window raids, including Hamburg and subsequent targets. loss rates on some operations as low as 1 to 2%, controlling statistically for distance, defenses, and weather. ORS attempts to disentangle contributing factors, bomber stream density, meteorological conditions, navigation aids, window deployment, and active jamming. The analysis confirms window as the primary variable explaining the reduction. RAF analytical studies describe Operation Gomorrah as temporarily ameliorating Bomber Command's travails over the Ruhr, with Chaff explicitly credited for reducing effective German radar performance. The language remains measured and technical, but the operational implications are profound. An ORS summary notes that window made it safer to go on operations, a conclusion that prompts some crews to volunteer for additional sorties while the advantage lasts. Planners standardize window carriage across the force. Production of metallised strips accelerates. Mass manufacturing, essentially a paper goods operation, can meet demand easily. The integration of window into standard doctrine proceeds rapidly. Every bomber now carries bundles as routine equipment. Dedicated electronic warfare support units expand. The concept of bomber support shifts from fighter escort alone to include electromagnetic countermeasures as an equal component. Bomber Command transitions from treating window as an experiment to incorporating it as an essential element of operational planning. Target folders now include window deployment instructions alongside navigation routes and bomb loads. But the loss curves also reveal limits. By early 1944, the downward trend in casualties begins to flatten. German tactics adapt. The rigid Himmelbett control system gives way to more flexible approaches. Zahme Sau, tame boar, tactics allow night fighters to operate more freely in the bomber stream. Wild Sau, wild boar, tactics rely on visual acquisition over burning targets. The Luftwaffe cannot eliminate window's effect, but can reduce its advantage through tactical evolution. The electronic duel becomes more complex. Simple countermeasures meet countermeasures. The cycle of measure and response that will define electronic warfare for decades begins over the night skies of Europe, October 1943 through March 1944. German night fighter headquarters and London air defense sectors. On the night of the 7th to 8th of October 1943, British radar operators near London notice anomalous clutter during a Luftwaffe raid. Narrow bands of echoes appear where aircraft density cannot explain the returns. The patterns match Window's signature. Controllers watching the displays understand immediately. The Germans are now using their own version. German planners had hoped that deploying Düppel would restore some offensive capability against Britain. Throughout 1941, the Luftwaffe night offensive, the Blitz, had inflicted severe damage before being stopped by improved British defenses, including radar-directed fighters and anti-aircraft fire. If Düppel could blind British systems as Window blinded German ones, perhaps a renewed offensive would succeed. The reality disappoints German expectations. With the Luftwaffe reduced to small bomber formations and the RAF possessing overwhelming fighter superiority, German chaff produces limited effect. Raids using Düppel, including the attack on Barry Harbor on the 2nd of December 1943, achieve tactical surprise but cannot restore strategic capability. On the defensive side, Germany manages to claw back some interception effectiveness. The adaptation depends not on a technical counter to Window, but on organizational and tactical changes. The rigid Himmelbett system, with its neat boxes and controlled interceptions, gives way to more flexible command structures. Night fighters receive broader zones of responsibility. Zahme Sau tactics, where controllers vector fighters into the general bomber stream area, then allow pilots to hunt visually, reduce dependence on continuous radar tracking. Wild Sau tactics push single-engine day fighters into night operations over illuminated targets, accepting higher pilot losses in exchange for more kills. The shift has measurable effects. By the Nuremberg raid on the night of the 30th to 31st of March, 1944, the combination of tactical changes, clear weather, and strong German fighter response produces 11.8% losses for Bomber Command, 95 aircraft from 795 dispatched. The figure exceeds even the worst Ruhr raids. It demonstrates that window alone no longer guarantees acceptable survivability. The Germans have learned to fight in a window-saturated environment. A post-war radar history emphasizes that German recovery from the initial Chaff shock depended largely on tactical evolution and increased fighter commitment, rather than any simple technical counter to window. The Luftwaffe could not remove window's effect, but could operate despite it. Controllers learned to distinguish patterns in the clutter. Pilots developed techniques for visual search in crowded airspace. The defensive system adapted to the new electromagnetic environment. Meanwhile, across the world, a parallel story unfolds. Japanese engineers have independently introduced giman-shi, deceiving paper, to jam American radars months before Hamburg. The principle is identical. The wavelengths differ, but the fundamental lesson emerges on both sides of the globe. Radar is not absolute. Simple physics can defeat complex electronics. The age of electronic warfare has begun. Night of the 5th to 6th of June, 1944. The English Channel off Cap d'Antifer and the Pas-de-Calais coast. German Seetakt coastal radar operators scan their screens as part of routine watch duties. Around midnight, returns begin to appear. The echoes show density and movement consistent with a large convoy, multiple ships advancing slowly toward the French coast in the Calais sector. The radar picture looks authentic. Range, bearing, and speed match expectations for an invasion fleet. Operators report the contacts up the chain of command. Coastal batteries prepare to engage. German high command expectations, shaped carefully by months of Allied deception operations, anticipate a major landing in the Pas-de-Calais region, the shortest channel crossing, the most direct route to the Ruhr. Every piece of intelligence, much of it deliberately planted, points to Calais. The radar contacts appearing on Seetakt displays seem to confirm the prediction. But the fleet is largely an illusion. The echoes come primarily from window, dropped by RAF aircraft flying carefully calculated patterns in operations codenamed Taxable and Glimmer. The real invasion fleet sails toward Normandy. Number 617 Squadron and other RAF units execute the deception. Small formations of Lancasters, 16 to 18 aircraft per operation, fly precise racetrack patterns parallel to the French coast. At calculated intervals, they drop window bundles. The timing and spacing are critical. Seetakt radar operates at specific frequencies with known resolution, approximately 520 yards. TRE scientists have determined that dropping chaff at 2-mile intervals along a moving track will create a continuous convoy-like return on Seetakt displays. The illusion depends on matching the radar's resolution limits and creating apparent motion toward the coast. The operations combine window with other deception measures. Moonshine jammers create false echoes. Small boats tow radar reflector balloons, Operation Filbert, adding to the Phantom fleet's apparent size. The layered approach exploits German trust in radar while undermining its reliability. Intercepted German reports and post-war analysis confirm that coastal units reported the Phantom fleets, calculated approach speeds, and in some cases opened fire on the false contacts. The deception achieves at least partial acceptance of the radar picture. An RAF history of Operation Taxable records that bombers dropping chaff in progressive patterns were able to create the illusion of a large fleet on coastal radar screens. The language is matter of fact, but the operational achievement is sophisticated. Window here serves not to protect a bomber stream, but to shape enemy operational decisions. The fake fleets reinforce Operation Bodyguard's strategic deception, supporting the fiction that Calais, not Normandy, is the primary invasion objective. German reserves remain positioned to counter the wrong threat. Hours pass before commanders recognize that the main assault is elsewhere. While German staff debate what their coastal radars are showing in the Channel, Japanese naval officers in the Solomon Islands have already used their own version of deceiving paper, giman-shi, to shield night raids from American gun-laying radars. The principle crosses oceans and theaters. Radar warfare has become global. May 1943 through February 1945. Solomon Islands, Guadalcanal, Iwo Jima, and selected Japanese home island installations. During a night attack on Guadalcanal in May 1943, United States Army SCR-268 gun-laying radar operators observe unusual clutter. Broad returns appear that do not correspond to the small number of Japanese aircraft reported by visual observers. The clutter patterns interfere with radar-directed anti-aircraft fire. Subsequent technical analysis of recovered material identifies 75-centimeter strips of reflective paper. American intelligence documents this as the first recorded use of giman-shi, literally deceiving paper, in combat. American expectations assumed that radar-directed anti-aircraft fire would provide a decisive advantage over Japanese night raiders, particularly in the Solomons where air superiority was contested. Japanese response comes from Navy Lieutenant Commander Sudo Hajime, who develops giman-shi independently of European chaff work. The strips are cut to jam specific American metric band radars, including SCR-268, which operates at wavelengths around 70 to 80 centimeters. The dimensional match is precise. Japanese air crews drop the strips ahead of formations to create false plots and confuse anti-aircraft fire. Japanese radar inventory remains limited throughout the war. Air warning sets exist in small numbers. Gun-laying radars are unevenly distributed. Integration into fighter control systems remains patchy. Most Japanese radars operate at meter wavelengths, longer than German or British systems, making them vulnerable to giman-shi, but also reflecting the technological gap. Japanese engineers understand the principle of chaff, but lack the industrial capacity to mass produce it or to upgrade radar frequencies simultaneously. Giman-shi sees first combat success in mid-1943 over the Solomon Islands. Operators judged the effect positive in reducing losses to radar-directed gunfire. Later use includes the Iwo Jima campaign in February 1945 and the Okinawa campaign from April through June 1945. At Okinawa, giman-shi supports kamikaze raids, attempting to confuse defensive radars long enough for suicide aircraft to reach their targets. Aluminium shortages constrain production. Even when giman-shi is available, quantities remain modest compared to Allied window use. American forces begin deploying their own chaff, codenamed Rope, in the Pacific Theater. B-29 superfortresses carry electronic warfare equipment developed from European experience. The Pacific radar war mirrors the European one. Both sides use chaff, both attempt jamming, both develop tactical responses. But the asymmetry in industrial capacity produces different outcomes. Allied forces can afford dense chaff deployment, multiple jamming systems, and rapid frequency changes. Japan struggles to maintain radar coverage and fighter fuel supplies simultaneously. A technical history notes that Japanese forces dropped 75-centimeter strips of deceiving paper, giman-shi, to disrupt the SCR-268 that was proving to be a problem. They considered the use successful in reducing losses. The assessment reflects limited success within severe constraints. Giman-shi works as physics predicts, but physics alone cannot overcome industrial disadvantage. When B-29s begin mass attacks on Japan in late 1944 and through 1945, both sides possess chaff. Only one side has the radar numbers, jamming equipment, fuel reserves, and industrial depth to exploit it fully. The mathematics of attrition, visible in loss rates and sortie counts, tell the rest of the story. Late 1943, Through late 1944, RAF No. 100, group airfields scattered across East Anglia. On a dispersal track, ground crew prepare an aircraft with an unusual load profile. Multiple aerials sprout from the fuselage, more than a standard bomber carries. Inside, mandrel and carpet jamming transmitters occupy space normally reserved for bombs. Large stocks of window bundles fill additional compartments. The bomb load is light. This aircraft's primary mission is not destruction, but deception and disruption. Early 1943 operational thinking treated window as a single technical trick. Each raid deployed one countermeasure in isolation. By late 1944, Allied planners view window as one component in a layered electronic warfare package designed to attack German air defense at multiple points simultaneously. The evolution represents a shift from tactical expedient to strategic capability. No. 100 Group exists specifically to coordinate bomber support and electronic warfare. The group's aircraft combine window for false targets, mandrel to jam Freya early warning radars, carpet to jam Würzburg tracking radars, and additional systems to interfere with German radio navigation and communications. The designers behind these systems, scientists and engineers at TRE and associated establishments, have created an electronic order of battle. Each jammer targets a specific German system. Mandrel broadcasts noise across Freya's meter band frequencies, degrading early warning. Carpet targets Würzburg's centimetric bands, disrupting gun-laying and fighter guidance. Jostle jams German radio communications. Piper rack interferes with navigation beacons. Window creates the false targets that overload any tracking system attempting to sort real bombers from chaff clouds. Analysis of specific raids in late 1943 through 1944 shows the combined effect. Operations with full electronic warfare support experience significantly reduced radar-directed interception rates even as German fighter numbers increase. The defensive system cannot compensate. Radar operators see screens filled with false targets and noise. Controllers cannot vector fighters reliably. Gun-laying systems lose track. Night fighter pilots report confusion and difficulty locating bomber streams. Some raids still suffer heavy losses. Nuremberg proves that no system is foolproof, but the average survivability improves measurably. A technical summary describes the evolution. Other radar-confusing techniques included airborne jamming devices, codenamed mandrel, piper rack, jostle, and carpet, all deployed alongside window. The integration marks the emergence of coordinated electronic warfare. Strategic bombing survivability increasingly depends on electromagnetic dominance rather than armor or fighter escort. The goal shifts from protecting individual bombers to denying the enemy the ability to use his sensors effectively. Radar transitions from an enemy advantage to a contested medium. The doctrine spreads beyond European operations. Across the Pacific, another strategic bombing force prepares to apply similar principles. The United States Army Air Force's Vestey Bomber Command, operating B-29 superfortresses from the Mariana Islands, studies European electronic warfare experience. Engineers adapt mandrel and carpet equivalents for Pacific frequencies. Window production begins for B-29 operations. The lessons learned over Hamburg and Berlin will soon be tested against a different radar network, the patchy, resource-constrained Japanese system defending the home islands. The electronic warfare principles remain constant. The industrial asymmetry will make the outcome even more decisive. June 1944 through summer 1945. Japanese home islands, Marianas, B-29 bases. At a coastal radar station on Honshu in early 1945, operators track multiple B-29 formations approaching from the south. The altitude is typical, 7,000 to 9,000 meters. The formation discipline is tight, but as the plots develop, the picture degrades. Additional echoes appear. Jamming increases across multiple frequencies. Operators struggle to maintain reliable tracks long enough to vector interceptors. The pattern repeats raid after raid. clear initial contact, progressive degradation, uncertainty at the critical moment. Japanese operational expectations held that expanding radar coverage and centralized fighter control would enable effective interception of B-29 raids. Plans called for early detection, timely vectoring, and concentrated fighter response. Reality falls short of planning. Radar coverage contains gaps. Fighter numbers are limited by fuel shortages and production constraints. Pilot training standards decline as experienced aviators are killed, and increasingly, American electronic warfare measures, including chaff and active jamming, degrade the radar picture at crucial moments. The United States Army Air Force's Bunty Orange Bomber Command integrates electronic warfare planning from the start. European experience transfers directly. B-29s carry window-equivalent chaff. Specialized aircraft mount jamming equipment. Tactics emphasize saturation and deception. Japanese radar crews face the same problem that German operators encountered over Hamburg, but with fewer resources to adapt. Japanese radar deployment remains modest compared to Germany or the Allies. Centimetric radar adoption comes late and unevenly. Command and control integration suffers from inter-service rivalry between Army and Navy systems. During night incendiary raids, the campaign that devastates Japanese urban areas through spring and summer 1945, interception rates remain low despite large bomber formations. Radar crews detect the raids, fighters launch. But effective interception requires sustained tracking and precise vectoring. Window clouds and jamming break the tracking link. Fighters search visually in darkness. Some intercept by chance. Most do not. The statistics tell the story. B-29 loss rates over Japan average around 2% across the campaign, lower than Bomber Command's losses, even with window over Europe. Japanese forces continue using giman-shi, particularly during the Iwo Jima and Okinawa campaigns. The strips remain effective against older metric band radars. But American centimetric radars, operating at 10 centimeter wavelengths, resist jamming by meter wavelength-tuned chaff. The technological gap widens. Japanese industry cannot produce the electronic components needed for frequency upgrades in sufficient quantity. American industry produces radars, jammers, and chaff in overwhelming volume. The industrial asymmetry that shapes every aspect of the Pacific War extends into the electromagnetic spectrum. A post-war assessment concludes that Japanese chaff was found effective at jamming metric band radars and confusing radar-controlled AA, but not efficient against centimetric radar. The statement highlights the gap. Japanese engineers understand the physics, Japanese forces use the technology. But without the industrial base to support rapid technological evolution, the effectiveness remains limited. By mid-1945, Japanese radar and fighter units face the same fundamental problem German crews confronted at Hamburg, operating in electromagnetic darkness for critical periods, but without the industrial capacity to compensate through massed fighters, rapid radar upgrades, or expanded production. The erosion of air defense capability accelerates. The mathematics of attrition grow increasingly unfavorable. Thin strips of metallised paper, combined with industrial advantage, help tilt the balance toward an inevitable conclusion. 1945 through the late 1940s. Allied post-war survey offices, British Bombing Survey Unit, and United States Strategic Bombing Survey departments. Economic and operations analysts compile data at tables piled with raid records, industrial output graphs, and radar deployment maps. Their task: quantify how electronic countermeasures affected the cost-benefit balance of strategic bombing. The numbers tell stories that narratives obscure. Before 1943, strategic bombing's viability remained in doubt. Could heavy bomber campaigns meaningfully damage industrial capacity before losses made the offensive unsustainable? Bomber Command's experience over Germany in 1940 through 1942 suggested the answer might be no. Loss rates hovered near thresholds that would exhaust trained aircrews faster than training establishments could replace them. Expansion appeared to offer diminishing returns. Then Window changed the mathematics. Post-war findings reveal complexity. Bombing effects on German and Japanese war production were neither simple nor uniform. Some industries suffered severe disruption, others adapted through dispersal or underground facilities. But the campaigns were sustained at intensity levels that would have been impossible without electronic warfare measures that reduced loss rates below break-even thresholds. Window and associated countermeasures kept average losses acceptable long enough to inflict cumulative damage on Axis industrial capacity. The analysts construct comparison tables. Bomber Command pre-Window loss rates, approximately 4 to 5% on heavily defended targets. Post-Window rates, 2 to 3% on comparable missions, with some operations seeing even lower casualties. United States Army Air Force's B-29 losses over Japan, averaging around 2% as electronic warfare measures mature through 1945. The reductions appear modest in percentage terms. But compounded across thousands of sorties, the difference represents thousands of aircrews who survived to fly additional missions rather than being shot down. Industrial metrics add another dimension. The Battle of the Ruhr, conducted at high loss rates before Window's introduction, is later assessed as negating German plans for further increases in production. Hamburg, the first major Window operation, inflicts severe damage at dramatically reduced cost in aircrew casualties. Later campaigns using integrated electronic warfare maintain pressure that degrades German transportation networks, synthetic fuel production, and ball bearing manufacture. In Japan, sustained B-29 operations destroy urban industrial capacity and disrupt logistics networks, contributing to economic collapse. A Royal Air Force review notes that the Battle of the Ruhr negated all plans for further increase in production, despite the campaign's high cost in losses. The assessment acknowledges that Window-enabled operations like Hamburg and subsequent raids maintained offensive pressure at sustainable loss rates. Without electronic warfare measures, the review implies, sustained strategic bombing at the scale achieved might not have remained statistically viable. The fundamental calculation is stark. Bomber production, crew training, fuel, ordnance, all represent significant industrial investment. Loss rates above certain thresholds make the investment unsustainable. Electronic countermeasures reduce losses enough to keep the offensive mathematically viable. The cost of Window production, essentially a paper goods manufacturing operation, is trivial compared to the cost of radar installations, fighter production, and air defense networks it disrupts. Post-war cost-effectiveness analyses reveal an asymmetry. Thousands of tons of chaff costing far less than the aircraft and crews it saves, versus radar chains and fighter forces costing orders of magnitude more, while losing effectiveness against simple reflectors. The conclusion is quantitative rather than rhetorical. Strategic bombing remained viable because electronic warfare made it so. 1946 through 1950. United Kingdom and United States defense research establishments. Early NATO planning circles in Brussels. A post-war evaluation report opens with a cost-benefit analysis. One column lists the monetary cost of thousands of tons of chaff, aluminum foil, paper, packaging, distribution. Another column estimates aircraft and crew lives saved by Window-assisted missions. The ratio is sharply favorable to the countermeasure. One analyst calculates that the entire Window program cost less than replacing 50 heavy bombers. Wartime perception treated chaff as potentially temporary. Surely radar designs would adapt to nullify the countermeasure. Frequency changes, better processing, Doppler discrimination, all might restore radar's original effectiveness. Post-war assessments reach a different conclusion. chaff is not a temporary trick, but a permanent element of electromagnetic warfare. As one of the most cost-effective electronic countermeasures of the Second World War, it establishes principles that will shape military doctrine for decades. British and American evaluation boards study the complete record. German and Japanese radar equipment is examined in detail. Captured documents reveal defensive thinking and adaptation attempts. The conclusion: chaff worked not despite radar sophistication, but because of fundamental physics. Radar depends on detecting reflected energy. Any object with appropriate dimensions and electrical properties will reflect that energy. No signal processing eliminates false targets if they match the physical characteristics of real targets. The countermeasure must come from other directions: different frequencies, different detection principles, tactical adaptation. Early NATO air defense committees incorporate these lessons into planning documents. Post-war aircraft designs include chaff dispensers as standard equipment. Naval vessels receive similar systems. The assumption shifts. Future air operations will occur in environments where both sides use chaff and jamming. Radar remains valuable, but no longer provides the unambiguous picture it offered before 1943. Electronic warfare becomes a distinct field, requiring specialists, doctrine, and integrated planning. Meanwhile, captured German and Japanese radar sets find new uses. Research establishments employ them for ionospheric studies and early radio astronomy. The dual-use legacy of wartime radar technology extends beyond military applications. Scientists who developed radar and countermeasures transition to civilian research. The electromagnetic spectrum becomes a domain of peaceful inquiry as well as military contest. A modern technical reference defines chaff as thin strips of aluminium intended to blind or disrupt radar systems, wording that directly echoes 1943 practice. The continuity is intentional. Despite decades of technological evolution, the basic principle Joan Curran demonstrated in a TRE laboratory remains operationally relevant. Later conflicts, including the Falklands War, where British ships used chaff against Exocet missiles, prove the enduring effectiveness. The essential lesson is unchanged. For every high-cost detection system, there may exist a low-cost physical counter capable of destabilizing it. The relationship between sensor and countermeasure defines electronic warfare through the jet age and beyond. 1950s through the present day. A retrospective view spanning European and Pacific theaters, extending forward through subsequent conflicts. Modern air defense exercises show chaff still being dispensed from aircraft and ships. The radar signature appears instantly on contemporary displays, clusters of false returns blooming across screens, mimicking the clutter German operators saw over Hamburg 70 years earlier. The technology has evolved. The physics remains identical. Original advocates of radar in the 1930s viewed it as approaching an all-seeing instrument, electronic eyes that could pierce darkness, clouds, and distance. Reality proved more nuanced. Radar provides extraordinary capability under many conditions, but it is not absolute. Its effectiveness can be sharply reduced by tailored clutter generated with simple, mass-produced materials. The Second World War demonstrated both radar's power and its vulnerability. Joan Curran receives recognition in post-war historical accounts and commemorations for her contribution to Windows development. Her work, initially classified and later overshadowed by other wartime technical achievements, is gradually acknowledged. Memorials and technical histories credit her invention. The oversight is corrected. Modern chaff differs in materials, aluminum-coated glass fibers rather than metallised paper, and in sophistication. Dispensers release strips cut to multiple wavelengths, effective against various radar bands. Doppler radars attempt to discriminate between moving targets and slowly descending chaff. Electronic processing tries to filter false returns, but the core physics remains unchanged. A half-wavelength conductor resonates. Radar cannot distinguish between metal strips and aircraft if both present similar electrical characteristics. The historical balance sheet can be summarized numerically. Battle of the Ruhr, 4.7% average losses across 18,506 sorties, a rate approaching Bomber Command's operational breaking point. First Hamburg raid with window, approximately 1.5% losses from 791 sorties, a reduction sufficient to make sustained strategic bombing statistically viable. Japanese giman-shi, effective enough against American metric band radars that its inventors judged it successful, but limited by aluminum shortages and technological lag, unable to reverse the attrition mathematics, favoring Allied forces. These figures support a concluding observation. In late war air campaigns from Hamburg to Tokyo, some of the most decisive shifts in loss rates and interception effectiveness came not from heavier bombs, faster aircraft, or revolutionary designs, but from centimeters of foil that turned clean radar images into noise. The strips forced German crews to operate in electronic darkness during critical raid periods. They degraded Japanese tracking systems already strained by industrial shortages. They demonstrated that sophisticated technology remains vulnerable to simple physics applied intelligently and at scale. The lesson extends beyond the Second World War. Electronic warfare in Korea, Vietnam, the Falklands, the Gulf, and every subsequent conflict relies on principles first demonstrated over Hamburg and the Solomon Islands. Radar and chaff evolve together, locked in a technical competition neither side can permanently win. The contest continues, but the fundamental dynamic established between 1943 and 1945 remains. Sensors enable capability. Countermeasures challenge that capability. Adaptability determines advantage. Thin strips of metal dropped from aircraft over dark cities and oceans helped reshape that balance when industrial democracies needed technical leverage against totalitarian adversaries. The foil descended slowly through searchlight beams and darkness, each strip reflecting electromagnetic energy according to immutable physical laws, turning technology against itself. On radar screens across 3 continents, the same transformation occurred. Certainty became confusion, tracking became guesswork, confidence became doubt. Some called it window, some called it Düppel, some called it giman-shi. But the name mattered less than the effect, the moment when operators realized their instruments no longer showed reality, but only its distorted echo.